Welcome to another episode of Hacked and Secured Pentest Exploits and Mitigations. I'm your host, Amin Malikpour. Today we are unpacking 3 real-world exploits that prove one thing. Trust is the weakest link. A forgot password IDOR for full account takeover, a shared session token flaw that let attackers reuse SMS logins, and a classic Java Deserialization to remote code execution exploit that turn unvalidated input into a server-side shell. Let's break them down. Have you ever tested the password reset flow and think, this can't be that simple to break? That's exactly what Chris Valad described in his write-up on Medium.com. He found an account takeover vulnerability hiding inside the forgot password feature, a classic place pen testers always check, but so often overlooked by developers. This is the kind of bug that doesn't need fancy payloads or a scanner, just careful observation. Let's break it down. First, what kind of vulnerability is this? It's an IDOR, insecure direct object reference, but not in the typical view someone's order way. Here, it was baked right into the password reset flow. Christie was hired to do a pen test on a web application. As always, he made sure to manually test every authentication flow. Tools are great, but this kind of bug is easy to miss if you don't think like an attacker. He started with the classic forgot password link. Click it, in thread, get the reset email. The email arrived right away. It had a link that looked safe. It was long, encrypted, and not guessable. Something like emaildomain.com/c/very long encrypted string. But when he clicked it, the link redirected him to another page on the main app. And that URL was very interesting. It looked like some endpoints/confirm.php ? U equals long number, T equals hash, X equal another number. That U parameter caught his eyes immediately. It looked like a user ID, a long numerical value. So he thought, what would happen if I change these parameters? First, he tried something simple. He removed the X parameter entirely and refreshed the page. Guess what? Nothing broke. The page still worked fine. No error, no session invalidation. That was his first clue the server wasn't validating the link properly. Then he took the next step. He incremented the U value by 1. And suddenly the page loaded, showing another user's email address in the reset form. It literally said, your email is another user at targetcompany.com, enter new password, confirm password. At this point he wasn't sure it would work. So he created a second account of his own in another browser. He copied that account's user ID from its profile page. Then he pasted that user ID into the reset URL. When he loaded the page, it worked. He was able to set a new password for that account and then logged in as the second account. That's full account takeover. No special tools, no code injection. Just changing a single number in the URL. Now let's pause for a second. What do you think the next step could be? You have just realized you can reset any account's password just by knowing or guessing their user ID. Why not trying random numbers to find other accounts? Or enumerating IDs to target specific roles? Christie did exactly that. He didn't just stop at one test account. He noticed the IDs were long but sequential. He tried decrementing the IDs down, guessing lower values to see who else he could hit. Eventually, he found the account of a high-level user. Even the CEO's account was within reach. That's the risk when IDs are predictable and access controls are weak. And here's another subtle flaw. The URL had an X parameter which was probably supposed to act like an expiry mechanism. If you removed it entirely, the page worked without it. That bypassed any expiration logic completely. So even old reset links could be reused. Let's talk about why this happened. The initial reset link in the email was safe enough. It used an encrypted long string. But when the user clicked it, the app handed over the keys, exposing raw IDs and insecure parameters in the final redirect. That's the mistake. They assumed encryption on the first link meant they were safe. But by trusting the client with direct access to sensitive parameters in the second step, they lost all security. So if you are designing, building, or maintaining applications, here's what to do. Never expose raw user IDs in password reset URLs. Use secure, time-limited tokens stored server-side that map to a specific user and expire after one use. Don't let users modify critical parameters. Validate everything on the server side. And test your own flows manually. Don't assume the design is safe just because it looked encrypted. And for pen testers out there, don't skip any feature. Always test password reset. Change every parameters you see. Remove them, increment or decrement them. See what breaks. Look for IDs that are predictable. This is where real-world account takeovers hide. No fancy payloads, no 0 days. Just curiosity and a little patience, and that's what makes all the difference. We started this episode with a forgotten password flaw that let you take over any account just by tweaking a single ID in the URL. But what if I told you there is another common feature that can go wrong in a similar way? What if the weakness isn't in the password reset link, but in the SMS login itself? That's exactly what yet another hacker found and shared on HackerOne. A flaw in a SMS-based authentication that let them hijack user sessions without ever knowing the victim's verification code. It's basically an authentication logic flaw, where the server trusted users too much during the SMS login process. Now let's dive into how this attack actually worked. In a typical SMS login, you enter your phone number, the server sends you a verification code by SMS, you type that code in and you are logged in. Seems safe, right? Here's how this application was designed to do the SMS login. When the user entered their phone number, the app sent a request to something like /session create. The server replied with a session token which was needed later along with the verification code to call /session verify and complete login. Everything seemed normal, right? So what do you think was the issue? The issue was that if the attacker also called /session create with the victim's phone number, the server gave them the exact same session token. No new token per request, just the same one over and over. Let's think about that. It meant both the real user and the attacker held identical keys. Neither one was valid yet, they still needed the verification code sent by SMS. But once the real user entered that SMS code and complete verification, that same session token became valid for both parties. Now the attacker had a fully valid authenticated session for victim's account. The only thing needed is to keep pulling the server to see if the session token suddenly became valid. The attackers could keep checking the session by calling an endpoint like /me. At first, it would return 401 unauthorized. But once the victim entered their SMS code, the same request suddenly succeeded, returning user info, phone number, even friend connections. From there, the attacker had full access and could make any other request the user could. This was full account takeover with no SMS code stolen, no phishing, just exploiting poor session management. Are you wondering why did this happen in the first place? Because the server didn't create unique session tokens for each request to /session create. It reused the same token for anyone who knew the phone number, meaning the attacker and victim ended up sharing it. Once the real user completed SMS verification, the attacker's copy of the token was just as valid. So for anyone building or designing authentication flows, here's what you need to do. Make sure every call to /session create returns a new session token. Send a new SMS code every time and invalidate the old one. Rate limit those endpoints so attackers cannot spam them. And don't assume that just because the user enters their phone number, they are the right person. And for my fellow pen testers out there, this is a classic case for manual testing. Don't just enter your own number and verify it. Try someone else's number. Repeat the session creation call multiple times. Check if the tokens are identical. See if verification for one user unlocks access for everyone who holds that token. It's the kind of bug no scanner will find. You have to think like an attacker. Look for places where developers forgot that two people might be holding the same key. And that's how real compromise happens. Not with flashy 0 days, but with quiet, subtle trust failures in the way systems are designed. At the end of the day, it only takes one shared token for attackers to walk right in. We started this episode with an insecure password reset flaw that let you take over accounts just by changing a number. Then we saw how sharing the same session token in SMS login let attackers hijack someone's session without ever seeing their code. But now, let's look at something even more dangerous. What if you could send a single request to the server and make it run any command you want? That's what Sia, one of our listeners, contributed to our podcast. This is a classic but a still very real problem with Java Deserialization. Now, for anyone listening who aren't familiar with this, let's explain. Serialization is a way to turn complex data, like objects in Java, into a format you can store or send over the network. Think of it like flattening a 3D model into instructions on paper so you can mail it somewhere. Deserialization is the reverse. You take those instructions and rebuild the original object. But here's the risk. If the server blindly trusts whatever serialized data you send, you can send instructions to build anything, even objects that execute code. Imagine a toy factory that gets blueprints in the mail. Normally they expect safe designs, like cars, dolls, or something like that. But what if an attacker sends a blueprint for a bomb, and the factory just builds it automatically without checking? That's deserialization without validation. So here's how Sia found the issue in the app he was testing. He noticed some endpoints in the app accepted large blobs of base64 encoded data in post request. That immediately looked like serialized Java objects. If you are a pentester and you see that, you need to pay attention. Sia intercepted the request with a proxy. He decoded the data and confirmed it had Java serialization headers, those magic bytes that Java uses to say, hey, this is serialized. That was the first big clue, but he didn't stop there. He tried sending random data to see what the server would do. The app crashed with a deserialization error. Error messages can be really helpful. They tell you what classes the app tried to load. In this case, the stack trace mentioned Apache Commons Collections, a well-known Java library with deserialization gadget chains. If you have studied these attacks, you know Apache Commons Collections is notorious for this. It has classes like Invoker Transformer that can be used to execute commands when deserialized. Alright. If you know the server deserializes untrusted data and it uses a vulnerable library, what's next? You craft a payload, right? Sia used Visoserial, a popular Java deserialization exploit generator. You pick your gadget chain, specify the command you want to run, like listing files on the server, and it outputs a malicious serialized object. Then he went back to Burp Suite, he intercepted another post request to that vulnerable endpoint. He replaced the normal serialized data with their malicious payload and hit send. A few seconds later, he got a response. The server had executed his command. He saw a directly listing of backend files. That's remote code execution. At this point, Sia controls the server. He can read config files, extract credentials, pivot into the internal network. Sia didn't go that far. He stopped at proof of concept. But this was enough to prove the risk was real. And it's worth saying, this wasn't some advanced 0-day. It was a known vulnerability in a library that's been around for years. If your app deserializes whatever users send without validation, you are at risk. So if you are building, designing, or maintaining Java applications, here's what you need to do. Don't deserialize untrusted data at all if you can avoid it. If you have to, use signing or encryption to ensure it hasn't been tampered with. Use libraries like Serial Killer to allow these safe classes and override object input stream to block dangerous classes. And always keep your dependencies up to date, because a single old library can open the door for full server compromise. And for my fellow pentesters out there, when you see serialized data, pay attention. Decode it, look for magic headers, fuzz it with invalid values and see if the server crashes or generates error. Test with Deserial or other tools to see if you can trigger code execution. These bugs don't always show up in scans. You have to look carefully. It's about understanding how developers trust data and how you can break that trust. Don't forget, it only takes one malicious object to take over an entire server. And before we wrap this one up, this finding came straight from a listener in the community. So if you came across something during a pen test, don't keep it to yourself. You don't need to polish it or write a full report. Just share what happened, what you tried, what worked and what didn't. We will turn it into something the whole community can learn from. You will find the Google form link for submissions in the episode description. Let's raise the bar together. Every vulnerability we covered today shared one lesson. Never trust what the client sends. From password resets exposing user IDs, to shared session tokens hijacking logins, to deserialization bugs running attacker-controlled code, each was a simple oversight that led to full compromise. And none of them would have been fixed without responsible disclosure. Because finding flaws is only half the job. Helping teams fix them is what makes the internet safer for everyone. If this episode helped you see security differently, share it with someone who is building, testing, or defending systems. This might be the one lesson that keeps their users safe. Let's make cybersecurity knowledge accessible to all. See you in the next episode.